So what I'm going to present is kind of a joint questions that we looked at with Anna Calisano that couldn't be here today. So I tried to cover like her domain as best as possible, and Xavier Penec was just here. So the idea was to extend the framework of Xavier on barycentric subspaces, but for a case where we don't have a manifold. So in such case, it's a priori not defined, but then we were quite close to define it still. So the question was like, okay, we can define it, but then how does it look like? Does it have nice property or not? Because we are losing a lot of smoothness, and of course this has some consequences. So just quickly, to motivate a bit this presentation and the questions. So barycentric subspaces, they were introduced in the context of the barycentric subspace analysis, which is a method to extend PCA to manifolds, which is actually a very different approach from the PGA approach, for example. And the idea was like, well, in PCA, what we can also see is that we're trying to fit a data set. We're trying to fit to a data set using some affine subspace. In the case of PCA, the affine subspace has to cross the mean also, but then we can interpret it like this, like geometrically. And so then the question was, rather than extending to manifolds the components, then we can maybe extend the notion of subspace and affine subspace. And that's how barycentric subspaces were introduced as a generalization to manifold of affine spaces. So spaces that are defined with a frame of points and not a frame of vectors. All right. So just very quickly, for a manifold Riemannian manifold, we can define the notion of exponential barycenter, which can be seen as a critical condition for a point to be a weighted Fresnel mean. And this was introduced before, actually, in the case of measures, so barycenter of measures. And then it's more this case that we are considering that was so introduced with together with barycentric spaces by Xavier Penec. So then once we have extended the notion of a barycenter, then we can just consider the subspace of all barycenters, and this will be the generalization of the affine subspace. So that's just how we get this definition. Then, of course, the structure of it is not as straightforward as the one of an affine subspace in the Euclidean case, but in Euclidean case they coincide. And if you look at constant curvature examples, so a sphere or a hyperbolic space, then, for example, hyperbolic space, a barycentric subspace of a frame of k plus 1 point is exactly the hyperbolic subspace of dimension k that cross all the points. So the notion is still like understandable in the simplest example and has some like coincidence with existing notion. Then completely moving to something else, but it's quite related. So why we were asking this question in the case of quotient spaces that are not manifolds? Because we were looking at a possible application of barycentric subspace analysis in graph analysis. So Hannah was looking at this question, and the story was a bit that she was writing things on the board, and then I saw it from afar, and it looks a lot like barycentric subspace analysis on quotient spaces. And I was also looking at it, but for a different quotient space that in my case happens to be a manifold. So everything was going very well for me and very bad for Anna. And that's how it started. So graph analysis, in the end, why it's so interested to look at barycentric space analysis, because we have this formulation of it that is called sample limited barycentric subspace analysis. And the idea is to consider frames that are only within the data set. So in the end, when we do this analysis, we retrieve a subspace that is described by some data already. So it's much more easier to interpret, and interpretation in graph analysis is very important and also usually very bad. So that was the goal of perform some of archetypal analysis. So that's why Hannah was looking at this method and really wanted to generalize it to graphs. Then the framework precisely that she considered is the one of unlabeled graphs, so which means that the nodes are unlabeled, and in the end you want to perform some kind of alignment because what you want to compare is the structure of the graph and not the labeling. So two examples that she gave me to illustrate a bit this question are, for example, comparing route maps of airline company. So you have just the example here of Lufthansa and Berja, and of course, you just looking at it, you're like, oh, these two airlines have very similar strategy. But if you compare the graph like this, of course, you need to align first to say so. So that's exactly what she was doing. And also another example would be like strategies in football game, how you arrange the players. So this context is very well known in the question of graph matching, when we want to reorder the nodes and just basically compute the distance between graphs. But we wanted to just extend this a bit beyond the distance and more as a graph space. That's what Anna did in her thesis. So she considered the graph space to be the quotient space of adjacency matrices by the group of permutation that are acting by conjugation, exactly reordering the nodes, as you just saw before. So this is a quotient space by finite group, and for this reason it's not a manifold, and that's where the problem starts. So Hannah has been working on extending, for example, PCA in this context, but using the approach of PGA, so especially tangent PGA. And why she can do that is because on such a quotient space, we can still define some notion of a logarithm, which is not the Riemannian logarithm, but it's very close to it in terms of interpretation. So I really don't know what time is it, but that's fine. Okay, great, perfect. So horizontal logarithm, that's how we call it, because it kind of looks like the horizontal lift of the Riemannian logarithm in the context of a quotient manifold. So basically the idea is to say we want to align two fibers and we want to find, given two equivalent classes, the vector that minimize the distance between the classes. And this is exactly the notion that we define to be the horizontal logarithm using a map called the alignment map. So we just align one class on the other, and we take then the logarithm of the exterior space. So here we have for example, in the case of graph, it's just the space of matrices. For example, symmetric matrices if we have symmetric graphs and so on. So exactly in this case of graph space, it's actually not so ugly because we have a very nice log, which is the Euclidean log. So it's just expressed like this, and it involves solving this graph matching problem actually. So it's still expensive to compute, but we can define it, and it looks a lot like a log. So then we thought, if we can define a log, then we can also define a barycenter, like exponential barycenter, and exactly using this critical condition that we had before, but now with the so-called horizontal log. So we have a condition for equivalence class in this quotient space to be barycenter, sort of a barycenter, and we can define a quotient barycentric subspace accordingly. This quotient barycentric subspace, you can also look at it as only its pre-image by the projection map, so that's kind of equivalent. But all right, so then a contribution, we especially look at the case where the top space is a vector space, because this is the case of graph, and because it's enough to see a lot of problems, so we don't need to go to a very complicated top space to see that it's going to be very hard to solve this barycentric subspace analysis question. And the critical condition, we can rewrite it as follow, and this gives us kind of an expression of a barycenter, but which is an implicit expression, because X will be the barycenter of the AI, the frame that we have, if and only if this actually X is also aligned. I mean, that if only if, sorry, all the reference points of the frame are aligned towards this X. And so it's very implicit, and in the end, it's meant that if you want to know if something is a barycenter and belongs to the subspace, we have to test every time if it's aligned, if like AI is aligned to X extra. So you can imagine that it's very uncomfortable to work with. But we still wanted to go until the end of the program. So we considered a very simple example, actually the simplest example you can look at where there is problem. And this is an example where our equivalence class are this, just reflection. So the action is just a reflection with respect to the central point of our domain. And on the right, this is the quotient barycentric subspace. So to be precise, this is the pre-image of it by the projection of 2 points, only 2 points. And there is some discontinuity. Why? Because this alignment condition that we had before is creating this discontinuity. So I think you need at least a bit more time than the time I'm gonna give you to understand why it's discontinuous, but we can come back to it later. Just to show that it's, yeah. So now the question, which is the central question in barycentric subspace analysis, is how we compute the projection on the barycentric subspace. And in this case, it's a bit hard because we need to know on which component of the subspace we want to project. And then we need to know if we actually are going to fall into this component or not. So there are 2 types of complexity. The first one is the combinatorial one, which we were expecting using a group finite group action, of course. But the second one that we were not expecting is that actually there is some geometric complexity that we have to know when the component ends or not. And we proposed to approximated algorithm just as a try, just to see if we could expect to work with this framework or not at the end. So the first algorithm, the idea was to align with respect to the closest reference point to our point project. And why we wanted to do that is because if we just noticed that if all the reference points, so the point of the frame, are aligned with each other, then the component is kind of maximal size. So then we were saying, okay, if it's on maximal size, then the projection has more chance to fall within the component. That was the first idea. So basically align everything like to chosen reference points, so including the data point, but also the other reference points. And second idea was to align rather everything to the point project. And why we wanted to do that is we were thinking, all right, let's say we project on the component. So when I say projecting here is using the projection of the top space, so orthogonal projection. If we miss the component with this projection, then we can just take the closest point, and it won't be too far because to start with, everything was aligned with respect to the pointer project. So that was the other intuition. And I mean, there is much more detail in the paper, but that was, I mean, we realized that the second one was actually doing much better in general. So this is an unfair comparison where the second algorithm is completely doing better. And what you see here is like when it gets red, it gets a very bad projection in terms of distance. And otherwise, when it's white, it's very good, like it's exact projection. So we actually can find the projection using the algorithm. So here what happened in this situation, which is quite an extreme case, is that we have taken the different component to be almost of same length, which meant that the first algorithm that was based on optimizing the length of the component is not useful, of course. Second case, which is another limiting case, where then we have a component of very small size. What happened is that the 2 algorithms around this component, they perform very bad, but they perform very bad equivalently. So, and then we concluded that the second method, so aligning on the pointer project, was better, but also that in some cases we would face a lot of mistakes. And this is just for a projection in a very simple example that is far from the complexity of the graph space. So what we concluded is that for the graph space, this is not so convincing that we are going to achieve something, but that it was also very nice to explore a situation where we have problems that is simple, and but we can still visualize. And it was also the first time that we explored a bit barycentric subspace outside of the manifold context, even if we discussed a bit with Xavier about some torus example, so with a discrete action, and there is also problems that you can figure out by yourself if you want to play around with it. We also figure out that the complexity actually, a combinatorial complexity in the graph analysis is so common that it's not something that we fear anymore, but the geometric complexity of the barycentric subspace was actually something that was very hard to deal with, and we decided not to. And for now and future work, we would want to contemplate other frameworks that are continuous frameworks, so Riemannian manifold framework. And one good example of that is a paper by Severin and also Jan Dryden that has actually been introducing some manifold valued graph analysis. So could be another solution to get back to the usual setting of barycentric subspace and then expect more nicer properties. Yeah.
Well, thank you very much. What a challenging topic. So, questions?
Yeah, I'd like to ask a very basic question just about barycentric subspace, even manifold. Suppose I'm interested in all such subspace of a fixed dimension. Is there a barycentric Riemannian?
Barycentric Riemannian. Wow, I don't know if this is a question for me.
I fix a manifold and I look at all barycentric subspace of dimension 2 or 3. Is there a barycentric Riemannian for that manifold?
Maybe Xavier, you want to answer this question? No?
Well, maybe that's more a question for you. It's really here. It's the, at least in what I understood about the barycentric subspace. I had to stop when we're getting too close to all the singularities that we can have. But the space of what we're really trying to do is doing some kind of optimization on the space of barycentric subspaces, and we can parameterize them with the basis, the points that we get, but there are singularities. So here is coming to maybe a question for you. Can you, or are there people interested to look at the singularities and what is the level of singularities that we're getting? Because this is a stratified space with lots of things happening. And maybe we are not equipped with the classical geometric tools to deal with that.
Is it actually clear how stratified it is? So what kind of stratification, like Whitney stratification?
There are several types of stratifications. One of them is if you get one point which is aligned, then you're getting to a low dimensional subspace. There's other one where you have points that collapse. If they all collapse together, then somehow we're getting to the principal geodesic subspaces. But if they collapse at different, you might have a subspace of points collapsing there, and then this is something new. So there's lots of singularities to describe there. So there's actually quite a lot of things happening. And there's also another problem, which is if there is some curvature, then each of the subspaces is different if you move slightly the points. But as soon as you're getting to something with zero curvature, like in the Euclidean spaces, then you have extra dimensions to remove. So you have quotient spaces to take. So this is unclear how stable things are.
So it sounds like, in general, this might not even be Hausdorff. Okay. Yeah, it looks like a great project to look at. Yes, more questions, please.
Thank you. Congratulations for the nice talk. I have a question which it's a beginner's question, but just about the way you define barycenters in manifolds, like in the normal case, is it easy to characterize numerically, or is it hard because you have the log at the point x that you are trying to target? So I was wondering how that works, even in the good case.
Great. I don't know if there are good cases. Well, I mean, that's a very good question. So let's say that compared to the Fréchet definition of a rated Fréchet mean, it's better, but for sure it's like numerically it's a very hard question. Like like this in theory we would say, all right, we would need some sort of a Newton method on manifolds to solve the equation, right? But then in practice we can get through minimum and so on, and we don't even know if it's unique actually to start with. But what is nice though is that having this implicit like condition is something that is very nice to include in larger optimization problem as a constraint. So it's a formulation that actually is, I don't know if I have time to give all the details, but if you want to perform the projection, for example, on a manifold, then you can express it as a constraint optimization problem on Riemannian manifold. So let's say this condition is still nice, nicer than just the weighted Fréchet mean definition, but I agree that in terms of numerical accuracy, there's a lot of questions that we didn't solve at all. So, yeah, that's my answer.
Okay, then thank you very much.
Thanks.